Our speaker today is Mike Romalachin. He's an application engineer from GE Multilin. A lot of you know Terry Smith, who is his supervisor, who did our presentation last week where we had a huge turnout. So good chance we'll have about the same kind of turnout today for Mike. Mike, I'll let you introduce yourself. If anybody has any questions, you can just add it to the chat box and I'll be monitoring that and we'll try and answer it appropriate then, or if not at the end. Go ahead, Mike.
Thanks, John. Hey, good afternoon, everybody. Well, at least for me, I'm in Eastern time. As John mentioned, I'm an application engineer for GE Grid Solutions. I work under Terry Smith. If you attended the conference earlier in the week, he's the one that did that conference. My background is the utility PNC, so I've worked for Con Edison in New York City for about a decade before I joined Alstom as a protection and control application engineer. And then now I'm a GE protection and control application engineer, specifically obviously on relays, automation systems, and such. My responsibility is providing any type of application support questions for customers on any type of relay design, relay application, relay setting, anything to do with protection and control. So with that, we'll get started on today's topic, which is network communications. Just briefly, today's agenda. We'll talk about some fundamental terms that you'll see thrown around anytime we talk about network communications. So just want to get you a little bit familiar with some of those terms as I go through the presentation. Then, before we get into the Ethernet networks, I just want to also briefly go into some of our legacy networks, specifically serial networks, which are still widely used today in a lot of industrial applications. For existing installation, a lot of brownfields still have serial communication, so it behooves us to talk a little bit about that. But the primary discussion today will be around Ethernet networks and the protocols that we use for our specific applications in the utility and industrial environment on Ethernet networks. So we'll talk about some of those protocols. And finally, we'll talk a little bit in not so much detail, but briefly introduce IEC 61850, which is a newer protocol. Well, not a newer protocol, it's been around for a while, but it's now starting to be used in a lot of applications for industrial and utility design. And it's a protocol that's built specifically for Ethernet networks. So we'll go into some of that. So in terms of the fundamental terms, what is a network? When I was creating this presentation, I was kind of saying, let me take a look at Webster's dictionary to see what they say about networks there. And the same term applies there, the same definition applies when we're talking about networking with people getting together and sharing information, sharing contact. It applies for computer networks, the same type of description, right? Set of devices connected together so they can share the information within each other. Usually the devices are computers, and so we refer to them as computer networks. So IT term, talk to IT guys and stuff, they'll refer to them as computer networks. But as we know in our industry, a lot of devices are mainly going to be IEDs or specifically relays. So we can also refer to them as relay networks because a lot of the devices on those networks are going to be relays. So why do we want to network devices? Why do we want to share information between devices? And that's to carry out a number of tasks that we need to carry out. And those tasks require the sharing of information. We'll talk about some of those tasks, but that applies to us in our industry. But in terms of the general industry, right now what we're doing, these video conferencing, if we weren't all networked together, we wouldn't be able to be doing this video conference. Sending emails, text messaging. If we're not all on network together, we won't be able to do that quickly and reliably. Such as also, sending printing, sharing printers on a network, scanners, so multiple people can use the same device. Sharing file and software. whether it's Google Drive or file share server, wherever that might be. And it also allows users to be able to access and maintain equipment on the network. So like for IT professionals, that's a big thing, to be able to connect to users while their network, be able to maintain. And for us, in terms of our industry, it's good to be able to, so you can connect to a relay and see what's going on with the relay if you have a problem. If it was a network, then you'd have to physically go in front of that relay to be able to do some basic maintenance. And when you talk to, in terms of the IT world, IT basically wouldn't exist without networks, right? Because we have all of these big networks, it forms the basics of communication for what the IT department supports. Some basic types of networks: the local area network, LAN for short, so we refer to it as. Everybody is probably familiar somewhat with these. You have them in your home, all your Wi-Fi, everything in your home, that's considered a local area network. So it's localized within one physical location. It could be a switchgear, it could be your home, it could be a substation, control room. And then we go to a wide area network. That's where we connect our local area network to, for example, to your ISP or internet service provider, which we refer to as the wide area network. And one of those wide area networks is the internet. So when we're connecting our local LAN to our wide area network, we're connecting our devices to the internet. And then we have some other ones that are like metropolitan area networks, which are basically between communities and cities. Private networks, enterprise private networks, for example, GE's internal network, that would be a private network, only employees of GE and GE entities can access that network, and it's shielded from the outside world. When we talk about backbone networks, these are networks that carry the bulk of the traffic. So for example, your ISP will kind of be a backbone network where a lot of people connect to that network to get access to the internet. And then we're talking about global area networks, where it's more like sharing of information within wide area networks, different wide area networks. This could be country to country, kind of bridging different wide area networks between countries to countries. Some of the key terms: the open closed system. I talked about the enterprise network, like within G. That would kind of be considered a closed network because it's only available to certain people. Whereas the open networks, like the internet, they're open to basically anybody that can have access to it. IP, a lot of people have heard about this term, Internet Protocol. It's basically to identify a device on the network. So we have all of these devices lying on the network. How do we identify them? The basic backbone of that identification is IP, which is a logical or virtual identification of that device on the network. Then we have the MAC address, which is the Media Access Control address, which is a physical address of the device to identify it physically. So, and we'll talk about, when we talk about IP a little bit, we'll kind of idea why we need to use IP. So the MAC is assigned by the builder of the Ethernet card. So when it manufactures the card, it's assigned at the factory, and that stays with that Ethernet adapter, Ethernet card, whether it's part of your computer, your relay, whatever device has an Ethernet communication port on it. Then, of course, I just mentioned port. Port is the physical access point in the device where you connect the device to. So on a relay, you might have a number of ports. On a switch, you're going to have more ports. You might have from 12 to 24 ports in a switch. Those are where you physically connect them. And nodes on the network are basically devices, whether it's your server, your relay. So those are considered nodes on the network. And then when we transfer data between devices on the network, we refer to those as network packets, data packet, payload information, a number of different definitions of description of that, but the basic thing is just data that we transfer over the network. Routers and switches are a basic part of any network design. Everybody is probably familiar with their router in their home. So whenever you connect to the ISP, you have a router in your home, which is a router is basically bridging two networks together. So it's bridging your local area network and your wide area network. Switches are bridging devices within the same network. So to be able to go from your local area network to your ISP, you need to use a router. But to be able to get from, for example, within your connected Wi-Fi phone to your printer in your local area network, you're probably using a switch for that purpose, or an access point, which is functioning as a switch. Network address translation is basically what a router does. So you have your local area network and you have all your addressing within your local area network, but that's only defined within your local area network. Now, to get out from your local area network to your internet, to get to the internet, you need to translate your address, or the address you need to get to, so it matches an address in the internet world. So that's what a router does. And usually how it does that, it has what we call a DNS server that it looks at, and the DNS server, because you're not going to type the IP address of what you need to access. What you're doing, you're tapping a web link. So for example, Google will be www.google.com. The router will look up in its DNS table what IP address is www.google.com, and it will make that translation, and it will connect you to that address. Within your network, you also might have what we call a DHCP server. So talk about these IP addresses that link, that identifies the device in the network. What this server does, it assigns those addresses. So anytime you connect to the network, instead of you having to go and manually type the IP address of your device, you connect to the server, and the server will assign it automatically, usually sequentially. So for example, if I'm assigned address 54, then somebody else connects a minute later, then they'll assign the next one 55, and so on and so forth automatically. Now, in terms of when we're creating relay networks, we usually don't use a DHCP server. That's usually manually assigned. So every time we set a relay, we have to go in and manually assign the IP address. But when we're talking end user devices like phones, computers, and stuff, those are automatically assigned by the DHCP server. And your router acts as a router and a DHCP server at the same time. So that's where it gets assigned at the router. Internet service providers are basically like your Comcast's, well, I don't know if Comcast is still around, Spectrum, Time Warner, Google Fiber. Those are your wide area network service providers that translates your LAN over to give you access to the internet. And obviously you pay probably a monthly subscription fee for that service. So some of the characteristics of networks, we'll talk about a lot of them. The topology of how devices are communicating. It could be a star, it could be a ring, it could be HSR. We'll talk about that, PRP, and the protocol that defines how those informations are shared between the relays. Because you can receive a packet of data, but if you don't know, it basically receives a series of ones and zeros, right? You don't know how to interpret that data unless you know what protocol that data was packaged under. So it's very important for all devices to interpret the data. They need to be speaking the same protocol. And then the architecture there's basically two basic architecture: peer-to-peer or one-to-one, basically connecting from one device directly to the other. And then there's a client server. So like your server could be like your SCADA system, and a SCADA might need to be connected to a number of devices in your substation to get the information. Usually client server, master slave, or one-to-many, same acronym for that type of architecture. So let's talk briefly about some of the legacy networks that we have out there. I say legacy because if you're building a new greenfield substation today, you're probably not going to use a serial protocol to network your devices. Most likely, you are going to use an Ethernet. But it's worth to talk about them because we have a lot of these sequential communication networks installed. So the advantages when they came out of using them, they limited number of connections. So you could have up to 2, like an RS-485 would have a send and receive pad. A 232 has about 4 or 5 wires, so there's not a lot of connections there. They can go long distances, obviously within limits. And they're simple interfaces and easy to implement. Like when you go in front of a relay, you want to download some settings on the relay, you either connect through an RS-232 directly to your computer and a USB. So it's a very simple interface to be able to connect to, and it's available physically for you there. The disadvantages of a serial network is its slow speeds. We can go up to 115, 200, but a lot of them use 9600 baud, so it's slow speed. One single protocol support, so you can only have communicating within devices one protocol, and that's one of the main advantages I'll talk about when we get into Ethernet, of supporting multiple protocols on the same data link or the same physical link. Limited bandwidth, so there's only so much information you could send, and that's why when you look at DNP and Modbus protocols that we'll talk about, we're looking at addresses, and we have to map addresses because we needed to save on bandwidth. So addressing was the biggest way of doing that, to be able to save on bandwidth. So all we need to do is grab the data in a certain address, and then we'd have to go and look up what that address is. So some of the newer protocols like 61850, it's not an address, it's actually a description. So it's a description of that address. So once you say, hey, I want A-phase current, and you go to Relay A will know exactly what A-phase current is and give it to you. You don't have to go say, hey, give me address 4001. You just tell it exactly what you need, and it will know what to give to you. So in terms of topology for serial, there's the point-to-point. So this is like when you connect your laptop directly into your relay, the front panel. Then you have your multi-drop, like your RS-485. So you have multiple devices daisy chained together. The disadvantage is using this multi-drop is only one device can occupy the communication with the host at one time. So you can't communicate to multiple devices at the same time. So you have to do some sort of polling. So you have to do some sequential polling to be able to get that data. So the protocols that we use on serial for legacy serial networks are DNP. 3.0 is the recent version. Distributed Network Protocol, it's now an IEEE standard, 1815. When it first came out, it was not a IEEE standard. The most common usage in our brownfield projects today is using it over an RS-485, which is that multi-drop architecture I showed previously. However, you could also use DNP if you have an Ethernet communication now, to be able to take advantage of some of the higher bandwidth that you have over Ethernet. So DNP the standard has been adjusted to include Ethernet as one of the communication mediums. So not to say that you have to use DNP in a serial, but it was built initially for serial communication. That was its basis. It now includes secure authentication, so you can authenticate and get the data securely. It is mostly used in electrical utilities, somewhat in industrial, but it's more electrical utilities. It's a master-slave or client-server protocol, so you have the SCADA that need to talk to multiple slaves. Some of the competing standards for our applications are Modbus and IEEE 61850 are the main ones. There are other ones like the IEC 101 and some more proprietary protocols like Allen Bradley and stuff, but we'll talk about standard interoperable protocols, and that's DNP is one of those protocols where if two devices are talking together, DNP, there's no proprietary information, way of sharing that information. It's a standard, so multiple vendors can support the same protocol. Some of the features, I talked about a lot of these, but just want to mention that basically what DNP over Ethernet is, how do we packet the serial data over into an Ethernet packet, and that's what it defines. Taking that serial data, putting it in an Ethernet packet, and transmitting it over Ethernet network. Similarly, Modbus protocol was designed for serial networks. Most common use is RS-485. It's mostly used in industrial applications. It is similar to DNP. It is a master-slave protocol. It does support Ethernet with the modern implementations, and it does also secure authentication, but in a different way. What it does, instead of creating its own authentication within the protocol, it's using Ethernet, which Ethernet uses an authentication protocol called TLS. It uses that to secure the information and send that secure information, encrypt it, and send it over. So it doesn't. There's nothing built into the protocol. It takes advantage of the Ethernet TLS protocol for security. Some of the features, I won't get into a lot of these, but again, in the data packet, it's same thing like DNP. It's basically taking that serial information, packaging it, sending it over an Ethernet packet. So another protocol that we use today is IEC 61850. It is an IEC protocol. It is a standard. So any vendor that implements 61850 should be interoperable between each other. And it's designed specifically for our industry. So it's for substation and industrial facilities, generators, distributed generators, wind farms, whatever. It's a modeling. It's not just a protocol. It's a language. So it defines like modeling of devices. Like for example, circuit breaker. How do you model a circuit breaker? For a generator, how do you model a generator? So it defines all of that, as well as the functions and engineering that goes into the function. So it's beyond just a protocol. It's, as I said, it's a language. And it's built around, the reason we did that is built around the fact that if we do that, it makes the protocol future-proof in terms of how does it support things that are coming up in the future. Because it's very flexible and it can adapt to any new technologies that we can introduce in the future. And for what we use it for mostly in our industry, obviously, is monitoring, protection and control, diagnostic information, event analysis, SCADA controls. So we use it for a whole host of things that it supports, as well as peer-to-peer communication between relays. It is defined entirely on Ethernet. So it is not a serial protocol. It will never work over serial. It is defined only for Ethernet communication. And so before we get into any more details of 61850, let's talk about Ethernet networks in terms of, since 61850 is designed for that, we need to know what Ethernet networks are and be able to identify them, create them, design them, so that we can support whether it's Modbus over Ethernet, DNP over Ethernet, or 61850. And the 61850, I don't say 61850 over Ethernet because by definition, 61850 is over Ethernet. So in terms of a historical perspective, as we know, going from electromechanical relays to microprocessor relays, we've evolved a lot in the technology over the past couple of decades. It's going from solid state to microprocessor base, increased sampling time, which gives us faster protection, more diagnostic information, more diagnostic for motors, generators, transformers, getting more information to be able to do all of that diagnostic. I was just on a call with my colleague the other day, and he was saying, hey, you know what, these days a relay is really a communication device doing protection functions, right? It's protection is probably so much anymore as the primary function of the device, but it's a box, communication box that does relay protection in it. It's we want to make it very flexible and easily adaptable. So we have multi-function devices. So we have multiple functions in the device so that we can easily adapt to conditions, easily deploy them. And then, and in terms of the, sorry, I skipped over that slide. Sorry. And in terms of Ethernet itself, it has been going the same way of microprocessors. The technology has been evolving in the past couple of decades, where today's everybody is exposed to Ethernet in some way, right? whether it's at your home, talking on your cell phone, connected to the internet from your cell phone. Everybody is exposed to Ethernet. So it's a technology today that's widely used, widely accepted, widely interoperable with many vendors, different vendors, right? From providers, from cell phone providers to ISP providers, everything, we could talk to each other because of the interoperability of the standard. And it's evolved, and it is still evolving today, so we can keep up with the evolution by using that standard. So what is some of the, the benefits of using Ethernet? One of the large advantages is it supports multiple protocols on the same data pipe or the same physical data link. So remember we talked about serial, it only can support one protocol. So if you needed to get SCADA information and then you needed to connect to the relay to get some diagnostic information that might not support DMP, then you might need to have another serial link to that device. With Ethernet, all protocols can be supported. Well, I shouldn't say all. Most protocols are supported over Ethernet. So it can, you could talk DMP, you could talk Modbus, so you can have different devices on the Ethernet network with different protocol, and they can all be able to talk back to your SCADA master, no problem, over the same data link. It's a mature technology, as I mentioned, and it is low cost today, because you want to buy a Wi-Fi router for your house, probably not going to cost you more than $100 today, right? But so it's a very, since it's mature technology, it's been around for a while, it's widely used, it's very low, it's low cost. It is high speed, high bandwidth. Some of today's, sorry about that, for some reason my computer keeps jumping slides on me. So the speed has been evolving. We started out with like 10 megabits per second. We're up to 100 megabits per second, and today's standard is basically 100 gigs when we're talking about actually direct wired. When we talk about Wi-Fi, we evolved from Wi-Fi A and B to Wi-Fi G and N. Now we're up to AC, and then we've recently released Wi-Fi 6, which is AX, which can get up to a couple of gigabytes of data on the same Wi-Fi data link. So technology is improving, and the bandwidth, the speed is improving for every time that we add new devices to the network. So it's constantly evolving, it's mature, so it's a good technology for us to use for our applications. So just to give you a brief introduction into some of the networking medias that we use over when we talk about Ethernet network. So it's a twisted pair copper cable we refer to usually as an RJ45, and fiber optic, which comes in a number of different wavelengths and the way they transmit the data, the light signal, multi-mode or single mode. So single mode is a more effective way of transmitting the light signal for longer distances, while multi-mode is more for shorter distances, and the wavelength, the higher the wavelength you go up to, the more distance you can transmit that light signal. And then the Ethernet interfaces, I talked a little bit about the 100 megabit, the 1 gigabit, and some of the Wi-Fi. And then, the physical connection, you need to have transmit and receive pads and such. So what is the advantages of using twisted pair copper or RJ45 over fiber optic? One of the main things is it's easier to terminate, obviously, the connector. It's lower insulation, could be lower insulation costs, because fiber optic, you might need special connectors, special splicing equipment, special skill to be able to work with it. Whereas with the Ethernet, it's not much special skill needed and not a lot of special tools needed. The disadvantages is it is susceptible to noise. So if you are going to use RJ45, make sure you use within a substation environment or industrial environment, make sure you use RJ45 with shields on them, and those shields are properly grounded. The length, obviously, it's limitation on the length that you can run that electrical, because it is a voltage drop issue, as with any electrical connection. One of the other advantages is it can auto-negotiate the speed that it needs to talk to. You don't need to change the medium. Fiber optic, the advantage is it can go long distances, very long distances. It's immune to any sort of electrical noise or interference within your facility. So usually you recommend, if you're going to install Ethernet network between industrial utility environment, which, as we know, are very noisy EMC areas, so you want to be able to have your data connection immune to that. So we recommend fiber optic. But if you do need to go small, shorter distances, then it's easier to use RJ45. Make sure you use shielded RJ45 cables. The disadvantage I mentioned, fiber optic, it's more difficult to terminate, splice. You need special equipment, special skill set to be able to do it. And you need special media ports on your devices. So instead of electrical ports, you need fiber optic ports and your relays and your switches. Some of the topologies, the most basic one is a star architecture. So basically everything connects into one switch, and then it gets connected back to my master in this example. So if that one switch fails, I lose communication. So it's not a very robust system. So single point of failure, you will lose communication. If you need to, on the drawing on the right, you can add some redundancy to it. So you can have a star redundant architecture, but that involves adding additional devices or switches. And recovery times in terms of switching from one device to another, it's about 3 to 5 milliseconds. So it's not very slow, but at the same time, it is finite. So if we go to redundant star architecture, we can provide some sort of redundancy, but at a cost where if we do that, we might as well go to some of the more robust architecture that I'm going to talk about. Like, for example, one is a mesh architecture. So with the mesh architecture, there's a lot of interconnections between the various devices so that a single point of failure on your connection or on your switch will only affect communication on a part of your network, not your entire network. The disadvantage of using this is the additional cabling obviously required to be able to accomplish this mesh. One of the popular one is the ring architecture. So this ring architecture, basically all the devices are connected in a ring. They don't go point to point like in the SOAR architecture. And it provides redundancy so that if you have a break in the ring one way, the data can be rerouted to go the other way. Or if you have a loss of a switch, the data can be rerouted to go over on the other side of the other switch. So it provides some redundancy without much additional cost from additional cabling, like the mesh architecture or the star redundant architecture. Using some proprietary techniques, the ring recovery, when you lose a connection to when you recover, can be up to less than 5 milliseconds. I think Cisco has some proprietary, but a lot of that are proprietary. There is one standard is called RSTP for ring architecture. So if all the devices are, if you have different manufacturers, you obviously want to use a standard, which is RSTP, to be able to do this architecture, because then you can't do a ring if you have different manufacturer and the one manufacturer implements a proprietary standard for the ring reconfiguration. So just some topologies that we could use within our environment. In this, for example, this substation topology here, we could do 2 ways. One is we can have Ethernet switches, or 2 Ethernet switches on each lineup, have the devices come to those switches, and those switches go back to our central location or central server. Or we could have switches on one panel instead of being segregated by the switchgear lineup, for example. We could have a dedicated communication panel where everything goes back to that panel. So obviously advantages and disadvantages of doing that. It's easier to implement one versus the other. The other one might be a little bit more reliable because one of these switches will not cause a problem in the network. So it all depends, you know, what are you looking for? What type of redundancy, what type of robustness you're looking for in a network when you're doing a design. Sometimes it's limited by the physical restraint, right? You might not be able to install switches where you need to get some sort of redundancy between in the system. The problem with these discrete Ethernet switch topologies is, as you can see, there's a lot of connections here, right? A lot of point-to-point connections. It requires a lot of point-to-point Ethernet cabling, which is not, for RJ45, probably not a big deal. If you're doing that, they might be within the same switchgear lineup, so the runs might be short, so it might not be a problem as long as you shield them. Might not be a problem, but when you're talking about maybe doing fiber optic and the lengths are longer, the runs are longer, then it might be more difficult because of all the splicing and running of that cable that you might need to do. And it does require physical space among the devices, so that needs to take into consideration. You might not have the space, or so you might need to be a little more imaginative to come up with space to add this piece of equipment. And when I'm talking about space, I'm talking about updating in a brownfield project. Obviously, if you're doing a greenfield project, you're designing this from scratch, you're going to provide the needed space for all the equipment that's needed. And of course, with more switches you add, the more things you need to configure in your network. The other technology that is out there today is the reduction in cabling. Is basically each relay is like a switch. So each device is like a switch. So you can go from relay to relay, create a ring architecture. So it reduces the number of hardware, the number of cabling, and such. So the switch is basically internal to the device now. So the relay or device has to have at least two switches, right? 2 ports, sorry. And most modern relays do, like our UR relays have standard 3 Ethernet ports. So our 8 series can come with up to 2 Ethernet ports. So most modern devices will give you this architecture. And not only that, it needs to be able to switch in a timely manner. So if there's a break in one of these ring connection, it needs to switch in the other direction. And it needs to do that in a way that's fast and also interoperable with if you have multiple different types of devices in that ring. And then one of the standards that we use for that is HSR, High Speed Seamless Redundancy Protocol, which is a protocol to create devices in a ring and be able to self-heal that ring, switch that ring seamlessly without any recovery time. However, the devices have to be able to support that standard protocol. So if the devices support that standard protocol, we can do this, and it becomes a seamless ring, and any break or recovery time is inconsequential. Now, we're talking about going to Ethernet networks, but we still have legacy serial devices out there, and legacy relays, meters, what have you, transducers, etc. And we still probably, when we do a brownfield upgrade, we're not going to upgrade the entire station at the same time. We might do something partially. So we might have an Ethernet network. But it is possible to have a hybrid Ethernet serial network. You don't have to basically scrap your serial network just because you're upgrading something and you want it to go into Ethernet. And there are devices that we call serial servers, the serial translators, to be able to do that, so they can translate that serial protocol into Ethernet version of that protocol. So we can have RS-485, 232, DMP, Modbus, and it can communicate to many devices, up to some of them can support up to 128, depending on the serial server or the serial transceiver device. They can take advantage of the fastest bandwidth. That might not be possible because your serial devices might not be able to handle that bandwidth. So it all depends. They can support the highest as well as the slowest bandwidth. Now, what this is saying with the port settings is remember when we talked about Ethernet, I thought each device is identified with an IP address in the network. The serial server is just one device in the network, so it's identified with a single IP address. However, it is technically many virtual devices connected to it. So how do I connect to all of those devices when the transceiver only has one IP address? And that's where the port settings come in to say, hey, where I need to communicate to the different devices, I might have different ports with different devices, different addresses to the different devices to be able to, I can connect to the serial server with one IP, but then I tell the serial server, this is the port I want to connect to, or this is the address that I need to connect to get down to the individual device. So, so you just need to connect to that one port on the serial device with one IP address, but you need to identify which device you need to talk to. The alternate to that is maybe you don't need to talk to those devices on the serial network. All you need to do is to gather the information. So what you could do is you could set up like a Modbus map or DNP map in your serial server and just access that map directly from the serial server, and then just have different locations in the address list for the different devices. But that requires more configuration and an additional device to be able to have to maintain with a mapping. So let's expand upon the RSTP protocol I mentioned. So again, this is a standard protocol. All of the stuff that I talked about today is basically standard protocols, standard information, so that when we have different devices from various manufacturers talking the same protocol, they can communicate with each other. So what RSTP is, it's saying you can connect Ethernet switches in a ring, and those switches basically need to detect failure in the ring and be able to recover when the communication path is lost for that ring. So what that does is basically the RSTP protocol, once everything's connected, it sends a message, each switch sends a message around the network to determine if there is loop in the switch in that network. And obviously, if your ring is connected and healthy, it'll find a loop. And when it finds a loop, it's not that bad, because if you have a loop, you could send two pieces of information down two separate paths, and they will basically collide with each other, and that's not good. So what it will do is it will logically disconnect one of the loops. So in this case, that one that has a shadow on it, basically, it's not saying that link is down. It's just saying logically within those switches are ignoring that link for now, because that creates a loop. And what it does is, if there's a break somewhere else in the ring, so if there's a break in the ring there, what it does then, it re-enables that loop with the shadow on it. So now it re-enables that loop, and now all the devices can connect to each other again. The issue with, not issue, but one of the drawbacks to RSTP is a finite time between when that loop breaks to determining when the break happened to the recovery of the other loop. As I said, some proprietary implementations. I don't like to talk too much about proprietary stuff, but it should mention that there are some switches out there that have proprietary protocol for ring architectures. So be careful when you connect them together. You got to be of the same manufacturer. But if they have RSTP, then it's not a problem. The problem with RSTP, the speed of recovery, it might be implemented differently in different manufacturers. So for us, we say about a couple of milliseconds, 3 to 5 milliseconds recovery time, but a different vendor might be a 20 millisecond recovery time. So you will only be, the recovery time, the total recovery time will be determined by the slowest device on that ring. But mostly, most switches should have a recovery time of less than 20 milliseconds that support RSTP. So when we talk about redundancy of communication or reliability of communication, if we want reliable communication, a single point of failure should not take us out, should not stop communication of the device. And most modern devices, or I should say all modern devices today, will have some sort of recovery mechanism for single point of failures. And in terms of our relay, we have up to 2 ports. We can have a primary, secondary port. Primary port is communicating, have a loss. Then you can switch to the secondary port. And that's the beauty of Ethernet, because it's monitoring the path all the time. It knows exactly which path is on, which path is off, and the decision that it needs to take. I just want to also mention that this is not just affected to Ethernet is not just a wired communication. It is a wireless communication also. So you can have, like in your house, you can have Wi-Fi. Within your substation, you can have Wi-Fi. We do have MDS. Was that a question, John?
Yeah. A chance to catch your breath. We got a really good question that came in from Tim. Recovery/rerouting. He wants to know if it's automatic.
Repeat that. I didn't get it.
Recovery reroute is automatic. Question.
Yes.
Yes. And
Yes. RSTP. Yeah. It's RSTP, HSR. Yeah. It's all automatic. Yeah.
He also wants to know if the switch has to be managed or you can do it with an unmanaged switch.
For most of these recovery mechanisms, you will need a managed switch, because there are certain settings within those protocols that you might need to set certain parameters. So yes, you will need a managed switch.
Would you like to?
Okay, thanks for that.
Sure, you weren't talking to yourself.
Well, I'm sure if you guys have not heard me, I'm hoping that you would have told me already. Anyway, so thanks for those questions. Hopefully we'll get more questions come in. We only learn by asking questions. So with the wireless, it's seamless to the relay. So like a wireless device like this is going to have its antenna, and then you just connect the relay. It's just an Ethernet port that you connect to, or you switch to it, and it's seamless to the end devices. Obviously, it's bandwidth limited and speed limited, because depending on the range, the wireless communication is going to be bandwidth limited, and there might be, depending on the type of technology that's used to get faster speed, you might need to use an unlicensed frequency and a line of sight communication to get the fastest and more bandwidth. So there's the disadvantages and advantages of using this technology. You could also use it over LTE. We have devices that can go over LTE, but again, speed and bandwidth is going to be an issue for LTE. I'm just going to speed up a little bit, because we're running a little bit behind, but I just want to mention also there's SONET network. So a lot of utilities create their own SONET network. So they create their own wide area network within their utility or facility, and these are accomplished using SONET multiplexers. So what multiplexers do is they can support any different type of communication circuits you need, whether it's voice, whether it's metering, any different type, SCADA, protection, any different type of communication on the same. So utilities create these SONET networks, and they put all the communication on it. So there's their backbone that could be relay. And with the newer technology like our JPACs, we have within it called MPLS technology. And what that is creating a dedicated link between one device to the next. So to the relay, it's seamless. So virtually, the relay thinks it's communicated from relay substation 1 to substation 2. So what that enables us to do, we could do line differential over these Ethernet SONET networks, because to the relay, it doesn't know that it's going through a multiplexer, because the multiplexer provides that dedicated path. And that's called MPLS technology. We have it in our JPACs and a lot of other manufacturers. It's a standard again. So it's just, we've just done some testing over it for line differential, and we don't see any issue with using it. It doesn't really add any tripping speed to the device. The speeds are still about what you would get if you have a direct communication. Virtual LAN, so you might need to segregate traffic within your environment. So you might need SCADA traffic, you might have engineering access traffic, you might have maintenance traffic, you might have HMI information, metering information, and you might need to separate these pieces of data out because you don't want them to get to certain parts of your system or overwhelming certain parts of your system. But you don't want to create physically separate networks for that. That's okay, because if you use a managed switch, then most managed switches will have what they call a VLAN configuration or a virtual LAN. So within your physical LAN, you can create multiple virtual LANs. And devices that reside on those virtual LANs only talk to devices within their same VLAN. So devices, for example, these engineering computers here, they will only talk to devices that are on VLAN 10. And same thing for these accounting, and maybe for security, you need data only in a certain VLAN. So you can segregate your data within your network even further by creating these VLANs. Within the Ethernet protocol, there is a quality of service. So each piece of data in the Ethernet network might be more important than other pieces of information. So you can create priorities to those messages. So what happens in a switch when the message comes in? If multiple message comes in to go on the same port, it queues this, the switch creates a queue of those messages. And so the first one that came in is the first one that goes out, and so on. But if, for example, message comes in that has a higher priority than the previous messages, what it will do, it will bypass the queue and to go to the top of the queue and get where it needs to go to. So messages, data that have higher priority will have higher priority within the switch to get where they need to get to. And that one of that is like goose messaging for tripping purposes, and we'll talk very briefly in a couple of minutes on that. I talked about redundant communication in the devices today. So it has a primary and backup. So if there is a problem, you can switch over to the primary or backup protection devices. You could be physically separate, or they could be logically within the same device. But the other more robust redundancy protocol is the PRP, Parallel Redundancy Protocol. What it does, it takes advantage of those two connections of those devices, which is called a dual attached connection, or DAN, dual attached node. And what it does is it creates you have to create two physically different networks, and each one of those ports connect to the one LAN A or LAN B. So if there's a problem in LAN A or any device in LAN A, basically your device will not be affected, and it's what we call the data transfer will not be affected, and what we call a bumpless recovery, where it's zero recovery time, because the device is sending information and LAN A and LAN B at the same time. So if there is a disconnection in LAN B, the information will just get there from LAN A. Okay, I'll skip over this one. So we're running a little bit of time. So just a little bit on, not so much a plug or any commercial thing with the slide, but make sure your devices know your switches, your routers. If you're designing with for an industrial utility application, we're pretty familiar with relays, right? Relays are substation hardened, there's certain EMC standards, certain IEC standards they have to meet. Make sure your switches also meet those standards, right? You don't want to, you're not going to go to Best Buy and get a switch from Best Buy and expect that to work in a substation environment. No. You need to have industrial hardened switches to meet all the normal standards. Basically, all the standards that a relay meets, the switch should be able to meet those standards too. As I said, treated no different than a relay in terms of how hardened it needs to be. In terms of diagnostics, there are certain protocols and stuff to do network diagnostics, as in syslogs. I'm not going to go through a lot of those, but there are diagnostic tools, as well as the switches having, just like a relay, have a alarm contact that you can use to be able to help there's a problem with the switch. And you should wire those out if you can to be able to tell there's a problem in the various parts of the network. Or you could use these network protocols, like I said, syslog, to be able to do diagnostics on a switch. Time synchronization is also important, and with there's a couple of different protocols that we can use to do time synchronization across our network. SNTP, or Simple Network Time Protocol, or NTP, Network Time Protocol, are the two basic ones. They've been around for a while. You just need a server to supply the time, the NTP time, and then it will synchronize it to all the various devices in your network. The drawback of using SNTP is the accuracy. The accuracy, it could be in a couple of milliseconds depending on the clock or the server that you use, which will, like certain application like synchrophasers, is not good enough. And process bus is not good enough. So you need something with microsecond accuracy to be able to do time synchronization for those applications. And with that is the IEEE 1588 PTP, or Precision Time Protocol, provides that accuracy. So this can be less than a nanosecond accuracy, microsecond accuracy, sorry, or 100 nanosecond accuracy. So with this NTP, it's the same as SNTP. It uses the network to supply this clock signal, and however, it is much more accurate. It can use for synchrophasers, process bus, any type of time critical accuracy requirements. The drawback of it is all devices in the network need to be supported. This is a hardware-based switching. So the relays need to support PTP in the hardware, the switches need to support PTP in the hardware, and obviously the clock or server needs to support PTP in the hardware. It's not something you can just upgrade a firmware and it will support it. It could support it with a firmware, but then the accuracy will not be less than 1 microsecond. To get that accuracy, it needs to be done at the hardware level. So some of the testing tools, a lot of you are familiar with be able to know if a device is communicating, the ping command, ipconfig, to make sure you're getting the IP address on your device configured properly within the same. Wireshark these are all freely available tools. They're also, proprietary tools that you can purchase to be able to do diagnostics, but these are the freely available. And Wireshark, I use Wireshark a lot. It used to be called Ethereal. And it's very, very good. It supports any different type of protocol, so you can diagnose any type of protocol, and actually breaks down the protocol for you. Instead of, you could see in this diagram, instead of seeing bits of ones and zeros, you actually see what's in the data packet, the actual data. So it can interpret the data for you, and it will determine what the protocol is and automatically break the data down for you, so you can do diagnostics in the network. So 61850 is the Ethernet-based protocol. What 61850 attempts to do is basically virtually model things within our substation. And in this example, I'm showing a modeling of a breaker. So a breaker with what we call is a logical node within the substation. And then we can model that, create all the aspects, the attributes that we need, like the circuit breaker's position, the controls, any metering, any CTs that might be part of that breaker. So we can model it in the virtual world, and then we could send that information. And if one device wants XCBR breaker number 5, I know exactly what breaker it is, and I know all the data that's contained in there. I don't need to know what address that data is contained. All I need to know is that breaker number that I need to connect to. So the objective of 61850 is to be interoperable, to cover all information that we have in our facility, down to from the large generators to small meters, to have a long-term stability for being future-proof for any newer technology that we might want to take advantage coming. Just to give you an example of a system architecture, so on the top part of this, where we connect to our SCADA, is what we refer to as station bus, is where all our SCADA, metering information, maybe like non-critical tripping information. And then we process is the interconnection from our relays to our process equipment like our breakers, transformers and such. And where we might need, where these data is critical, like CT, VT information might be we're getting from our process equipment. That's critical information that needs to get there. These station bus to process bus does not need to be physically separately, but usually they are. But it is a logically, or they should be segregated. One of the applications of using 61850 is via goose messaging. This is to transfer fast peer-to-peer messaging between relay to relay. So we're talking about 2 to 4 milliseconds response time from relay A to relay 3, and then once you add the trip contacts and all the input recognition, all that stuff, we're talking about less than a cycle response time from when I initiate relay 1 to when I get a response from relay 2 to trip the breaker. So very fast communication means of doing it over Ethernet communication. And some of the applications that we can apply this to is breaker failure. When I need to initiate breaker failure, you know, if I need to broadcast tripping, like if I have a bus differential, the bus differential trip, I need to trip multiple breakers. I can broadcast that message to multiple breakers to be able to trip it without having to wire anything into those trip circuits. Main time main transfer schemes, instead of doing the wiring, I could do it over communication, load shedding, zone interlocking, relay voting, a number of reclose initiation on the frequency, load shedding, transfer tripping, and all sorts of applications, not limited to the ones. These are the most common ones that I have up here. So with that, we kind of went a little bit over. I'll skip over some of these, but want to say the benefits I mentioned. It's more of a object-oriented language, or a language where it describes a lot of various aspects that we use, and the advantage is high speed, a lot of data that we can transfer over it with it. We can do monitoring, diagnostics, protection tripping, getting CT, VT information directly from the substation yard without wiring CT and VT cables out there. So it gives us a lot of advantages, and future-proof. It takes advantage of current technology, specifically Ethernet technology, to be able to do that, and we expect Ethernet technology to evolve and 61850 to evolve with it as we go forward. So in summary, obviously Ethernet has become very popular networking technology, low cost, high bandwidth, and the support that it has in the industry. Everybody uses it, right? The number of network topologies and different network topologies that we can use to be able to achieve what we need. If we need something simple to something very robust, we have the topologies and architectures to be able to do that. Redundancy, failovers, all we talked about that we can do with that. And it also holds other advantages of having like VLAN support, quality of service for link loss and link loss alert, and all of that, where we can make intelligent decisions based upon these various standards that are available over Ethernet technology. With that, we can, if anybody has some questions. Sorry about going over a couple minutes later. John, you still there?
Yeah, I'll unmute myself. Great job, Mike. And I want to thank Michael McClellan for putting this together for us. I do not see any questions showing up. If they do, of course, they can contact you or contact us. And we probably have the
I sent Mike my contact information. I don't know who had sent it out in the email, but I did not include it in this presentation here. So if you want, you might want to, whoever attended.
Yeah, we definitely have your contact information.
Okay.
Would you send me, I recorded this, so would you please send me a